Okay, let us continue our second lecture. So last time I gave a Hamiltonian description of classical mechanics, introduced the notion of Poisson bracket, described its properties, and gave a very brief introduction into quantum mechanics. Let me go on just a little bit further. So I'm not going to repeat the properties of classical mechanics. Let me speak about quantum mechanics. So the basic principle of quantum mechanics is the following. Quantum particles are described by their wave functions. That is to say, elements of the Hilbert space H, where you can imagine that H is equal to either the L2 of R, square integrable functions on real numbers, a real line, or L2 of some measured space omega, or even more abstract L2, small L2, a space of square summable sequences of real or complex numbers, doesn't matter what, of complex numbers, okay. Then observable functions of our particles. They're just some physical values, some physical properties of the system, like temperature, like velocity, like, I don't know, coordinate, like pressure or something like this. They are all functions of coordinates and moment of particles in classical situation. So in quantum situation, observable functions are replaced by operators on this space. So that the value of the observable function on a particle is replaced by the average value of observable operator f on psi, which is equal by the following scalar product. Let me put it in a more mathematical way. So I take the vector psi and take its scalar product with f of psi. So if we work in this model where we consider square integrable functions, and this is equal to, so this is denoted by f in angular brackets with subscript psi, and it will be equal to the integral over omega of psi bar f psi d. I forgot bar last time, I think. Okay. So we go on, and one can ask what are the analogs of other ingredients of Hamiltonian mechanics in case of quantum mechanics. One important ingredient of Hamiltonian mechanics was the Poisson bracket. So in classical case, in Hamilton case, we have Poisson bracket as the operation which takes two observable functions and sends them to another observable function. it had three properties. First, it should be skew-symmetric. It should verify Leibniz rule and should verify the Jacobi identity. So one can ask whether such operations exist in case of operators in a Hilbert space. It turns out that there exists only one operator which verifies all three properties like this. That is the commutator of two operators. Let me briefly explain why this is the only operation which there is with these three properties. It is the commutator is, when we take A and B and take a difference of AB minus BA. The fact that this operation verifies all three properties is almost evident. As far as Leibniz is concerned, it's just something as simple as this. A times BC is equal to ABC minus BCA. It is equal to AB minus BA times C plus BAC minus CA. And that's precisely the Leibniz rule we look for. Jacobi identity is also verified very easily. And the most interesting fact about this is that there exists no other operation with this property, at least if we assume that it is continuous with respect to the operator norm. Let me briefly explain why it is so. Since we assume that everything is continuous with respect to operator norm, it is sufficient to work with finite dimensional. It's not sufficient. Let me start with finite dimensional case. So, if the dimension of H is less than infinity, that is to say, then the operators of H are given by matrices, and by M matrices with complex entries. And one can ask what operations there can be that would verify these three conditions. So let me denote this operation by B, and when we plug into it two matrices, B is already taken, so let it be O operation. So it should be verified this minus O BA, but what is more important, it should verify the Leibniz rule. If we fix A, we see that this operation O sub A is a map from matrices to matrices that verifies the Leibniz rule. But it is easy to see, and we'll talk about this when we come to the study of Hochschild cohomology, that the only operation on A, only set of operations on matrices which verifies this condition, it consists of so-called inner derivatives, namely O of A should be equal to operation which sends every matrix B to certain the commutator, certain matrix O of A and B. Where O is a map from matrices to matrices, linear map. Now, since the operation is skew-symmetric, since this operation is skew-symmetric, since O of AB is equal to minus O of BA, we see that O of AA is equal to 0, and hence O of A belongs to the centralizer of A. And the centralizer of a generic matrix consists of all polynomials and functions of A. It's closure of the space of polynomials with values in A. Now, on the other hand, any polynomial that linearly, so if we now compare this statement with the fact that this expression is linear in A, we conclude that the polynomial should be linear. And hence, O of A should be equal to lambda times A plus mu, where lambda and mu are certain constants. On the other hand, lambda, so mu commutes with everything, so we can actually forget about it. And it means that the only that an operation we look for, this operation will be proportional to the commutator of A and B. And that's complete proof. So roughly speaking, when we work in matrices, there exists only one operation which verifies this condition. But so when we go from matrices to genuine operators on a Hilbert space, one can either use some kind of limit procedure to go from finite dimensional case to infinite dimensional case, or use some continuity properties. Or you need to prove that something similar to this holds for the operators on Hilbert space. So this statement is based on the use of Hochschild cohomology. In case of Hilbert space and Hilbert operators on Hilbert space, you can a very similar result, but in that case it's a bit more complicated. So we see that if we really want to reproduce in some way Hamiltonian mechanics in quantum world, we really need to replace the Poisson bracket by the commutator of two operators. So let me continue. Observables are replaced by operators, and the Poisson bracket by commutator. Finally, let me recall that Hamiltonian mechanics, the main equation of Hamiltonian mechanics had the form df dt for all observable functions equal to minus the Poisson bracket of f and the Hamilton function h. Now this, if we look into it naively, this should be replaced by the equation df dt, so that is to say we consider operators dependent on time, equal to minus the commutator of f and h. H is the operator corresponding to the Hamilton function of the system. Here I actually omitted some important factors like h bar divided by square root of minus 1, I believe. But it is a mathematical tradition to omit these factors, at least for a time being. I'll definitely omit h bar, and I'll probably always omit square root of minus 1 in my lectures. Although I don't know, sometimes I'll probably restore them, but in mathematics they're not important. You can say that in mathematics we assume that square root of minus 1 is either absorbed by h bar or that it is equal to 1. It is also possible to say. It's a bit awkward, but it's the case. Now, as I explained last time, the main quantization problem is to identify the operators that should correspond to one or another observable functions. In some situations, it is sufficient to know the operators that correspond to the coordinates on our classical phase space. For instance, if our classical phase space M is equal to R2 with coordinates P, momentum, and Q, the coordinate of the point, with the only commutation relation verified by this coordinate system, that is to say P, Q is equal to 1, then in quantum case we need, for starters, we need operator P capital that will correspond to the momentum, Q capital that will correspond to the coordinate, and the condition we have here, which is usually assumed to hold, should be P, Q equal to 1. As I explained last time, it is not very hard to find the operators P and Q on smooth functions that verify this commutation relation. For instance, you take P equal to d over dx and Q equal to x multiplication by x, where H is the space of smooth square integrable functions. For instance, Schwarz functions on R. Again, let's look at it like this. And the commutation relation that P and Q verify is precisely as this. That's because for every function f, P of Q of f is equal to d over dx of x times f, which according to the Leibniz rule is equal to f plus x times d f dx. That is to say, f plus q of p of f. So if we want to restore some other function from these two operators, some other operator from these two, we can do this in many important cases. For instance, if our Hamilton function is equal to p squared divided by 2m plus or minus u of q, and it was the original Newton mechanics. Then we can, in quantum world, consider the operator h bar equal to capital P squared divided by 2m plus u of q. What is u of q? Well, if u of q was a polynomial, then you can just take the polynomial of the operator q. But if it were not a polynomial, you can just use some kind of functional calculus on operators and define it. And you use it in a very natural way. However, in many situations, these Hamilton function and more general observable functions will contain monomials of more general form. Say, for instance, Pn times Q. And then this monomial is not equal to Pn minus 1 times Q, because in fact it is equal to Pn minus 1 times Q times P, because in fact it is equal to Pn minus 1 times Q times P. Plus Pn minus 1. This doesn't mean much, because if you restore the original physical approach, we would have h bar here on the right, and this h bar is considered to be a very small value. It's something like 10 to minus 27 by the size of its, this is Planck constant, and it is very, very small. If I'm not mistaken, it's minus 10 to the minus 27th power, very small value, very small constant. However, so roughly speaking, the difference between these and these is very, very small, but it's non-zero. And therefore, the way you introduce this expression is very important, and that's the algebraic, that's the quantization problem, at least its algebraic side, because in addition to algebraic side of quantization problem, there exists a very non-trivial analytical side. And that's due to the fact that if we, as I explained, these two operators, if we take this kind of representation for these operators by differential operators, they cannot be applied to functions in L2 of R, because functions in L2 of R are in general not smooth. So you need to work hard to give some reasonable meaning to this representation. And when you try to do this, you will observe very quickly that this pair of such operators, P and Q, which verify this kind of commutation relation, can never be taken to be continuous in the sense of mathematical, in the sense of analysis. Either the one or both operators in this pair should be unbounded. In fact, this is called Wintner's theorem. Very simple fact, but still worth it. If P and Q are operators on Hilbert space, that verify this kind of relation. P commutes with Q by 1. I'll forget about this small value, small number h bar. Then either the one of them or both of them is unbounded. Both of them. The proof is very simple, in fact. We start with, we assume that the opposite is true, that is to say both P and Q are bounded, and then hence they have some module. For instance, module of P is equal to X and module of Q is equal to Y. Both are finite. Then, if you remember, module of an operator in a Hilbert space is defined by the supremum of modules of AX, where X is a point, is an element in Hilbert space of unit norm, supremum of norms. And it follows almost immediately that the norm of A times B is, I think it is, I don't remember, should be equal to norm of A times norm of B. Hence, if we take the norm of P to the power n times Q, it should be equal to x to the power n times y, right? Okay. On the other hand, so if we take the commutator of p to the power n q, it is easy to compute. It is equal to following sum by Leibniz rule. Using the Leibniz rule, we have this Pn minus 1 Pq plus Pn minus 2 Pq plus and so on plus Pq Pn minus 1 plus Pq P to the power n minus n minus 1. So altogether we have n terms here. Each term has the form P n minus 1 because this commutator is always equal to 1. And hence we have this formula and we can compute the norm. I'm sorry. I think it's actually inequality, like this. It's not equality, it's inequality. But what is true is that p to the power n, the norm of p to the power n should be equal to n. Okay. So what we have here is the norm of the commutator p and q is equal to n x n minus 1, right? Just by this. On the other hand, norm of this commutator can be estimated from some other, in some other way. Namely, it is equal to the difference p to the power n q minus q p to the power n. And by inequalities, we have it is less or equal to x n times y multiplied by 2, because this is less or equal to the sum of p n q norm plus q p to the power n norm. So we have inequality. This is less or equal to twice x n times y for all n. Since our operator is non-trivial, so x is not equal to 0. Hence we have that n is less or equal to twice x and y, x times y, which cannot be true unless either x or y or both are equal to infinity. So it means that even analytically, the construction of the quantum mechanical systems is quite a formidable task. So the theory, in fact, it is true that the theory of, well, strict, rigorous theory of quantum mechanics is still, I think, if not open, that quite an active area of research and it involves lots of delicate constructions, like because you need to work with unbounded operators, and this asks for lots of delicacy. Okay. I don't know. It is classically well-known fact that it follows from the basic principle of quantum mechanics that either the momentum or the coordinate of a quantum particle cannot be determined. So it is impossible to determine both these values simultaneously. I don't know. It appears in my lecture notes, but I don't know if it is necessary to speak about this at the lecture, because this is a well-known fact. I think it's a good exercise for everyone to prove this from the basic principle of quantum mechanics, but it's not the thing we are going to discuss today. Well, in the end of my lecture, if I have some time, I'll probably speak about this. Either that's what they call Heisenberg uncertainty principle. But now let us go on a little bit further. So we have, oh yeah, a little bit before we proceed, let me do one more thing. I told you that the Hamilton mechanics, the basic equation looks like df dt is equal to minus the commutator of f and h. In quantum mechanics, this takes the form of the equation df dt, d capital F dt, is equal to the commutator minus the commutator of f and h. This is what they call sometimes the, I think it's Heisenberg approach to quantum mechanics when we write down the equations on observables. However, in many textbooks, instead of this equation, Heisenberg form of equation, people prefer to work with Schrödinger equation, which deals with the wave function rather than with the observable function. It is probably more advisable, in fact, just because wave functions are thought of as usual functions, at least when we work with the standard representation of quantum mechanics by square integrable functions on a straight line. So let me show you that these two approaches are equivalent, in fact. Let me, to this end, let me write down the function, wave function psi, which will depend on coordinate x and on time as well, on time t. So this is the family parameterized by time of observable functions. And let us observe that df dt applied to psi, this is an operator, but applied to psi, it will be equal to the following thing. It will be equal to d over dt applied to f times psi, f applied to psi, minus f applied to d psi dt. So what do we get from this? Substituting this into the equation, we get on the we do the same thing on the right, and we get h comma f applied to psi, which is equal to h of f of psi minus f of h of psi. And it follows immediately by comparing this left-hand side and right-hand side, which should be equal by this equation. We see that the corresponding equation verified by psi is d psi dt is equal to h of psi. You see, this is true for all observables. This is true for all observables, this equation. And hence it should be true on the nose. Now this equation up to the scalar factor on the right or on the left, which looks like 1 over h bar times square root of minus 1, I think like this, d psi dt is equal to h of psi, is called the Schrödinger equation. It's much more popular than this one. Which is sometimes called Heisenberg equation. Usually, Schrödinger equation is usually postulated, whereas the Heisenberg equation follows from it by this kind of transformation. Okay, let us now speak about various methods to construct quantization. I begin with the classical canonical quantization, which begins by defining p equal to d over dx and q equal to the multiplication by x. If you're familiar with Fourier analysis, you'll see that these operators can be obtained by combining the direct and inverse Fourier transforms. A function f in Schwarz space. Schwarz space is a space of smooth, rapidly decaying functions. Then you can apply Fourier transform to f. And I always forget the coefficients you need to write in front of it. Let me take a look into my notes to make sure that yes, so here it is. So if we work with in Rn, in R1, then it is just this. F of f, f capital of f at a point x should be equal to 1 over square root of 2 pi integral over r of phi of psi e to the power minus ix dot psi d psi. And the inverse transform It could be, sorry, not phi, it should be f. Inverse transform, and apply it to G. Again, at a point x should be equal to 1 over square root of 2 pi integral against R of G of xi e I x xi d xi. In some, I heard that in some textbooks the role of direct and inverse Fourier transform is inverted. So I prefer to use this minus for the direct Fourier transform and plus for the inverse Fourier transform. Thus we define operator associated with some function a of pq, or more generally of x xi, as the operator which, when applied to function u, will give the function given by the combination of these three operators. First, you take the Fourier transform of u, then you multiply this Fourier transform by a, and then you take the inverse Fourier transform of the resulting function. It is easy to see that so in coordinates, this operator, let me write it down in coordinates, op a of u is equal to integral over R2 this times e to the power 2 pi I x minus y times xi u of y dy dxi. This is the canonical way to obtain apparatus which gives you this pair when you apply it to A equal to just x and A equal to just psi. So psi goes to, as far as I can understand, goes to d over dx, and x goes just to the multiplication by x. Or vice versa. It doesn't actually matter much, but I think it is like this. This is what we call canonical quantization. It's nice and has lots of good properties. It was used in the beginning of 1920s before the work of and Weyl. I observed that even though this formula is nice and simple as any formula involving Fourier transform can be, it has one important drawback, and it is like this. It is let us return to the origins, to the beginning. We have phase space M of the phase space of our Hamiltonian system. And we have functions, observable functions in it. Well, it is in physics it's physically meaningful to consider complex valued functions. It is used in many situations, but in between these complex valued functions, there exist real valued functions. They play an important role because they are functions which actually appear in everyday life, more or less. So when we go from classical case the quantum case, functions are replaced by operators, observables, as I explained. Operators. So one can ask, what should be the image of real-valued functions, real-valued observables? Now, as I explained, average mean value of functions, can be restored as this kind of thing, with this mean value of the operator. Every operator in complex world with complex numbers has eigenvalues. So if psi is an eigenfunction, then what we have here will look like lambda times 1, because I explained that every wave function of a particle should have norm equal to 1. So it means that the average value of the observable f will be equal to its eigenvalue when you plug into it an eigenfunction. In physics, one regards these average values as average values of the quantum observable, and hence these average values should resemble the values of the original observable function. If our function was real valued, it would mean that this average value should also be real. And it would mean that our operator, quantum observable, that plays the role of the given real valued observable function should be self-adjoint, because only self-adjoint operators have real eigenvalues and no complex eigenvalues. However, one can check that it's not always true that in this formula real valued functions turn into self-adjoint operators. Well, this is not a good example, of course, because even though this is not self-adjoint, but in fact this is easy to amend. You can replace it by square root of -1 times d dx. Then the joint operator p dagger will look like minus square root of -1 d dx dagger, but d dx dagger is minus d dx, and we have minus times minus is cancelled out. It cancels out. So this is in fact self-adjoint. However, if you take, for instance, something like I think it should be x squared times x times psi, I think. It should be something like this. This will not be self-adjoint at all, even if you restore the square root of -1 at its proper position. So to amend this, Weyl suggested the following trick. Instead of this formula, we will use a bit different formula. So the condition, or goal probably, change the quantization so that the canonical commutation equation, commutation property, and commutation relation that is p times q commutes by 1 multiplied by some factor holds, still holds, but real valued functions give self-adjoint operators. So here is the formula which Hermann Weyl came up with. Let me store it. So instead of sending every function a of x psi to the operator given by the formula which I've just erased, we'll send it to the operator, op sub w of a, which we applied to the function u, comes up with the following formula. I have integral over R2 e to the power 2 pi I x minus y psi a of x plus y divided by 2 comma psi u of y dy d psi. As you see now, x and y show up both in this formula in the parentheses as the argument of a, and therefore one can prove that the operator. So next time I'll talk about why this is in fact is self-adjoint. It's not very hard, but I just prefer to talk about something else right now, okay? Let us instead talk a little bit about the consequence of Weyl's approach. Namely, let A and B be two functions with proper decay on infinity probably better to put R2. So they depend on a. Effectively, yeah. I think it is time to restore a dimension to its proper place. It will involve introducing certain coefficients. Instead of 1 over square root of 2 pi, we should take 1 over square root of 2 pi to the power n, but that's not very much. So let us consider two functions, and let us consider the following thing. Take the operators we obtain from A and B, and take their composition as operators. It is easy to see that it's again an operator of the same form of A, I don't know, circle B. The same can be done for instance, just a moment. The same can be done for operators of Weyl operators. In case of Weyl operators, we can write down the right-hand side as a large integral. It's integral over, again, up to some coefficient here, which I omit. It is equal to the integral over r to n cross r to n. Sorry. It's equal to the operator of certain new functions a and b. And these new functions a star b can be written down in the integral form. If I take, so it's operator, it's function of two operators of x and psi. Remember that, right? So I'll abbreviate x and psi to one common letter z. For instance, here, let's begin with a circle B. This formula can be written, this can be written in a very nice way. A b of z will be equal to, okay, of x and psi will be equal to the integral over r to n cross r to n e to the power minus 2 pi I eta times y a of x psi plus eta b of x plus y psi dy d eta. That's the formula for this. As far as the second formula is concerned, it has a bit more symmetric way, and that's why we can, so here in this formula I cannot use this notation z, because you see this argument and this argument, they are different. Here we add eta to the second part of the argument, and here we add y to the first part of the argument. But in case of Weyl quantization, the situation is much more symmetric, and we can write down the same integral formula as follows: minus 4 pi I omega of z minus z prime z minus z double prime a of z prime b of z double prime dz prime dz double prime. The only piece of notation which needs to be explained is this omega, but that's pretty simple. As I explained, z is a point in R to n. Z is a point in R to n, which you can regard as the Cartesian product of Rn and Rn. If we denote, so this consists of psi, this is f, x and psi, and omega of z prime z double prime will be equal to the scalar product of x prime psi double prime minus x double prime psi prime, where I take the usual scalar product in Rn. So you see, this formula is much more symmetric, and hence we can actually use this formula to expand it in the form of formal power series. So the idea is very simple. We replace our usual commutative observables by quantum non-commutative observables by using Weyl's formula. In non-commutative world, the multiplication is given by the composition of operators. So we can regard this formula as a reflection of the composition of operations in the world of functions. So we have functions, we obtain operators, we go to another operators, and then we return to functions. So if we take the product of operators, it gives us some formula in functions. So this formula gives you the composition of operators expressed in terms of certain algebraic constructions in the world of functions. This formula is nice, however, integration is very non-algebraic construction. So to make it more algebraic, people prefer to go from this formula to formal power series. Let me do this, and that will be the last thing I'll talk about today, because this new formula will in fact be the formula of Weyl quantization, which will be our object of study for the next lecture. So to this end, I'll first eliminate 2 pi I and restore h bar in this notation. So I'll use the following formula. A star B is equal to 1 over, we'll eliminate 2 pi from this notation altogether, but I don't know. Okay. But in front, I have to introduce it in the front of everything, because it's change of coordinates. You see, I change these coordinates. I remove it from here and introduce h bar here, but this comes on expense of introducing some term in front of the integral. So let me rewrite this formula in these new terms, in this new form. Okay, so we need to put it into the power 2n, because the dimension of the space is 2n. And now we have double integral over r to n of e minus 1 over I h bar omega z minus z prime z minus z double prime a z prime b z double prime dz prime dz double prime. So I rewrote this formula so as to eliminate all 2 pi i's in front, and that it's here in the powers of E. Now I'm going to use the following popular way to introduce Dirac delta function without doing any kind of analysis. That's what people sometimes call Fourier transform of Dirac delta function. So if I take f of delta and I consider it and calculate it at point x, and I can do it in a very natural way, minus 2 pi I x psi delta of psi d psi. Now by the properties of delta function, this is equal to the value of this expression at point psi equal to 0, so it is equal to 1. And hence we can try to represent delta as the inverse Fourier transform of 1, which is of course illegal because this integral does not converge at all, but we can do this at least formally. Now I'm going to use this to unravel this formula a little bit further. So I'll omit the factor in front of the integral, and I replace the term I integrate inside with the help with something new, but using delta function. So instead of this integral factor, I'm introducing delta function of this sum zeta minus z plus z minus z double prime, sorry. Yeah. Okay. This means that we can actually replace the term here by zeta z minus z prime. You see the change of sign here. A of z prime, b of z double prime. D zeta, d z prime, d z double prime. So this integral is over r to n to the power 3, because I introduced this formal variable zeta just to be able to introduce this delta function here in the middle. Now I will denote this zeta. I replace it by something new. I'll introduce the matrix pi. Pi is the matrix inverse to the matrix of omega. So this omega is a bilinear function on R to n. So it's given by some matrix. In this case, this matrix looks like this. This is identity matrix minus identity matrix and 0 elsewhere. So pi is the inverse of this matrix. And now denote zeta by pi times k times h bar. And I replace delta function eventually by this formula. This will give us the integral over r to n in degree 4. E to the power I h bar pi of k plus z minus z double prime, e to the power k I k z minus z prime. This is change of variables, you see. A z prime, b z double prime, Oh, I forgot to put q here. This is, you see, you have here two variables, x and q, x and psi. So I have, and now I have four integrals: dq, dk, dz prime, dz double prime. Now it remains only to identify delta functions again and direct and inverse Fourier transforms here. For instance, if I take this factor, this kernel, integral kernel, I can rewrite it as e to the power I h bar pi of k times q times e ik z minus z prime. And that's because, you see, omega, we can actually have this because pi is inverse of omega, so omega cancelled out. Sorry, I had it here. Yeah, I had it here. I forgot to write it here. So you see, when we substitute pi here, omega cancels out. And same e I q z minus z double prime. Now, if we take this and multiply by this, it will look like the direct and inverse Fourier transform of AZ. And same here. And in the end, so direct and inverse Fourier transform actually cancels out, and so we just get AZ and BZ. And in the end, we look here and we recall that Fourier transform sends the multiplication by x phi to the partial derivative with respect to x, and vice versa. So we expand this expression in formal power series and use the corresponding differential operators. So in the end, we'll get the formula of the like this. We have exponent of the operator h bar times pi times d over dxi d over dxj. So x is a generic form to write down coordinates here. This x on the left is not this x on the right, because I and j here vary from 1 to n actually. So this x is just the coordinate in Rn, and this x is a coordinate on R2n, and this is just for the sake of brevity. Then we apply it to A and B. The left leg of the tensor product we apply to A, and the right leg we apply to B. And then we multiply it what obtained. So this gives us a formal power series expansion of this star product. That's the original idea of Weyl quantization, of Weyl product. Next time I'll speak about this in detail, and today I think it's time to stop.